Welcome everyone to the tutorial section of the ANN workshop. Over the last few videos, we covered a bunch of topics ranging from BNN, ANN, forward pass, activation functions, mean squared error and cross-entropy, gradient descent and backpropagation. And now it's time to put all the learning into some practical use. This tutorial you would be learning how to build on a one-layer ANN with mean squared error and gradient descent, and also building a one-layer ANN with cross entropy and gradient descent. At the end of this video, we would also have an assignment for you, which would be due on the 29th of October, and there are some amazing Amazon Prime gift cards waiting for you. So make sure to give an attempt to the assignment. It will not only give you some great prizes, but also it's a very good practice to put all your knowledge, learning into some practice. So let's start with our first example, which is building a one-layer ANN with mean squared error and gradient descent. I believe mean squared error was a topic which was covered by Nick in his supervised learning workshop. If not, you can, if you don't remember, then you can just go watch those videos, get your concepts around MSE clear, and then come back to this tutorial section so that it's easier for you to follow along. So let's get right into the tutorial. So our first example, we build a one-layer ANN. To start with that, we first import the math library, because there are lots of mathematical operations that we would need to perform, so we would have to import math. So first we were given data. We declare a variable x, and this is the data that we have given to it. The first column is usually the bias term, and these are the values that we give it. Now t is a label, and labels are basically the desired output. So you want your data to be transformed to 0, 0, 0, 1. To do that, first we initialize some weights. So we have given some weight as 1, minus 1, 1. We give iterations as 50, learning 10. So iterations 50 here means we will be making a loop, and the loop would be iterating for 50 times, and it would be learning 10 times. So within 10 learnings, it should be able to transform this data into the output that we need. So let's make a function called simple ANN with our data, with the weight, with the labels, iterations, and learning, all the parameters that we have initialized here already. Then we start off with declaring an empty list, and then we start our for loop. So for I and range of iterations. So this is an iterator and iterates for 50 times since iterations is already defined as 50. Now we make two empty list. Error is an empty list, and y, it's just this would be what our output would be. We would want this to be, because when we want to print y, we want it to return 0, 0, 0, 1. So we would make this an empty variable and keep empty list, and we would keep appending into it. So we make another variable for n in range of length of x. So length of x is this, and it would keep iterating over the entire length. And what we have to do is we have to calculate the weights into the data. So we keep multiplying. So we have two loops. One loop is for going over the rows, and the other loop is for going over the columns, and we keep on multiplying the weights to the data until we get our desired output. So this is a continuous process, and to that we and to this empty variable, which empty list, which we have to print out, we would keep appending this sigmoidal activation that we would be we would be applying sigmoidal activation over V. V over here is the multiplication of weights with the data. So when sigmoidal activation, if you remember clearly, is probability, returning probability either 0 or 1. And since we want it in the form of 0, 0, 1, we would be using sigmoidal activation here. And then we would use the MSE classification error to calculate what our error is, and accordingly backpropagate if there are any differences in the output. So we would be calculating our error here. This is the formula for the classification error, and then we calculate the gradient descent to compute the new weights, and then we sum up the classification error, and then we return y, w and e. Okay, so now let's print y and see what's the new, let's see what our one layer ANN looks like. So now we have printed it, and here is what our one layer ANN looks like. So this is one way of making a one layer ANN. The other way of making a one layer ANN is using cross entropy and gradient descent. So let me first explain the concept of cross entropy. Cross entropy is commonly used to quantify the difference between two probability distributions. Usually the true distribution is expressed in terms of one hot distribution. So it's basically in like a tabular format, and there are some values. I mean, the machine learning algorithm just gives a prediction to each label based on what label you want as an output. So suppose we have three labels A, B, C, and I want my training to give me my answer, my output as label B. So you can so basically it should be label A having 0%, label B having 1%, and label C having 0%. So we can interpret the true distribution by seeing that the training instance, the machine learning algorithm predicts it such that you would have 0% probability for being class A, 100% probability for being class B, and 0% probability of being class C. So that's what cross entropy is, giving 100% prediction to what your output should be. So to do the same thing, to build a one layer ANN with cross entropy and gradient descent, the whole idea remains the same. The entire code is the same as we saw above. The only thing that is different is the formula that we've used here to calculate the cross entropy classification error. Previously we were doing the mean squared error classification error, and what we're doing now is a cross entropy classification error. Either ways, when we print y, we would see that our values 0.4, 0.48, all of that is exactly same as what values we have received here by making use of MSE. So there's nothing different. It's just that there are two different ways. You can make use of two different ways for building a one layer ANN. And what the second line of output is just printing the classification error. It's just for your own understanding. It's not really important, but y is the one layer ANN that we have built upon. So let's make a one layer. Let's actually explore few data sets and see how we can make use of ANN in that. So we would be using the iris dataset, and to load the iris dataset, we would be using sklearn.dataset to load the iris data. So from sklearn.datasets we import load iris, and there are features and labels in every dataset which we need to make use of. So we would take features and labels, and we would load iris and we would return it true. So the x values would go into features and the y value would go into labels. So the iris data is 150 samples spread across 3 classes: iris setosa, versicolor, and virginica. And there are main 4 important features that we are going to use. So that's the sepal length in centimeters, width in centimeters, petal length in centimeters, and petal width in centimeters. We would be using this to visualize our data. So let's start simple and we would pick up 2 of the classes and perform some binary classification with our sample code, and we would select iris setosa and iris versicolor to start with. To start with the classification, we first use a NumPy library. So we import NumPy as NP, and then NumPy has various inbuilt functions. We would first try to make an array which has a range from 0 to 100, and we would put all of that into a variable called indices. And now we would set up a matrix, and this would be X, and np.zeros is basically a matrix with just zeros in it, and those zeros would be of the length of index. So X would have the same size as that of index, but would just be filled with zeros. And so now we want to take out the features from the X matrix. So this would be from scratch from the 0th row until 1 until 5 columns. These would be our features. And then we add our bias column to the X matrix, which would be from scratch until the 0th, like the first, as you know, the first column is our bias columns, and here we would be doing NP1. So our first one would just be ones, first column would be only ones, and it would be of the same length as that of indices because both of the matrices are basically the same. And now we do the same thing. We give labels are basically the output, and then we have some random weights that we give it, iterations, learning, and then we do the entire thing again as we saw in the above example. And then we use the cross-entropy classification error here because we were basically trying to visualize between 2 different data sets. So cross-entropy is used to quantify the difference between 2 probability distributions, and that's why we would use cross-entropy classification error here. So now after calculating the cross-entropy classification error, we would now calculate the gradient descent to compute some new weights, and it's the same process all over again. And now we want to print our new array. So let's see what we have. So here is our set of values, and we can say we are able to successfully classify iris setosa and iris versicolor. So this was for the first example we made use of setosa and versicolor. For our next example, let's use versicolor and iris virginica. So the entire code remains the same. The only difference is in the range, and we do the entire code all over again. And now let's run it, and here is our bunch of code. So you can see that it's not been classified well enough, like the data hasn't been visualized well. So for that, you can see the performance on the iris versicolor and virginica was not as good, and to do so we would try to visualize the data. For visualizing the data, the best way to do so is by making use of some plots to figure out what the difference is. So let's make a plot for the first example, setosa and versicolor, and then we would make a plot for versicolor and virginica to see what the difference is. So we start with the NumPy library, and now we would make use of the matplot library to make a plot. So we use the indices array again, same range 0 to 100, there were some features and labels that we had used, so we're gonna make separate variables for them, and each feature name would be sepal length, sepal width, petal width, all of that. And we just try to get how the plot function works. So we plot the figure of size 5 and 4. So on the x-axis we would have 5 until 5, and on the y-axis we would have until number 4, and then we're going to use some scatter plot, and we'll have a color bar beside the plot to see the differences in the scatter plot. And we would label x-axis as the feature name of x index, so that would just be the feature name from here, and the y label would have some feature name from here. And now let's run it to see what a plot looks like. So here you see there's a difference in the versicolor and the iris setosa. So that's why there was a good performance. But now if we see iris versicolor and iris virginica, the same process all over again, but we change the range again 50 to 150 just as we used previously, and we run the code here, and we see all of the data overlap each other, so that's why there was a difference in the performance. So you saw that there was a non-linear separation, and our one layer ANN was only successful when one of the binary classification when there was only one of the binary classification combination. So a one layer ANN is unable to handle some non-linear separations. So to address this, we introduce a second layer known as a hidden layer. And how do we do this? So we follow the same process as we do it with one layer. We write out the separation for the forward pass. We give an error term. It can stay either mean squared error or cross entropy. And then we apply the gradient descent now to 2 layers of weights rather than 1. So first we would consider the forward pass for a 2-layer ANN. We could use a sigmoidal activation function to keep things consistent with our earlier example. Note that the activation function will be applied once on the hidden layer and also on the output layer. So computing the gradient with respect to the different layers of weights will become more difficult, but it's still manageable. There are just some additional terms in the chain rule. The second layer weight will be almost identical to what we computed for a one layer network, except the input layer would be a hidden layer activation. So we have some fun mathematical exercise for you by making use of the PyTorch library, and wherein we would be building on an artificial pigeon brain such that it would recognize different digits. So that would be our next video. Make sure to look at that to see exactly how we could train an artificial pigeon brain to recognize some digits. So this is the end of this video. We have an assignment for you. We would want you to build a 2-layer ANN, and definitely you can take a look at the entire process that I had described to you earlier. You could use the same thing, write forward pass, MSE or cross-entropy or gradient descent, and do the same thing to develop a 2-layer ANN. So this is the assignment for you, which would be due on the 29th of October, and we have some amazing Amazon Prize gift cards waiting for you, so make sure to do it and submit your do it on Colab, and then send a Colab shareable link to the email down in the description, and we would be giving out Amazon gift cards to the best creator of a 2-layer ANN. Go through the code well enough. If you have any questions, make sure to ask in the MIST101 channel on Discord, and try to finish it as quickly as possible so that you could get your Amazon gift card. Thank you.